Hello, and a very welcome everybody to my project presentation. The topic of my project presentation is investigation of properties and hydrocarbon potential of reservoir rock using petrophysical evaluation method. This is basically a case study of horizontal well in southern North Sea. The project was supervised by a lead petrophysicist, Ms. Daniela Krasanik, whereas simulation software support was provided by Logicom ENP. The presentation consists of introduction, history of the field and operational summary, literature review, software methodology, manual methodology, outputs from offset wells, results, discussion and interpretation of results, conclusion, recommendation and references. Introduction. The background of project describes drilling and evaluation of complex nature of thin reservoir rocks using LWD tools. The first part of problem statement is selection of appropriate evaluation methods for complex radioactive sand sequence, whereas the second part discusses the selection of reliable true formation resistivity to overcome the issue of polarization horns. The aim of the project is to have grasp and understanding of evaluation of complex lithology reservoirs, making reliable choice of true resistivity formation in thin reservoirs, and use of standard simulation software. The objectives of project includes building of raw log plots, selecting suitable petrophysical parameters and analysis methods, selecting cutoffs for volume of clay, effective porosity, and saturation of water. Finally, determine the original gas in place per unit area at reservoir conditions to make financial decisions. History of the field and operational summary of the well. The history of the A12 field involves its discovery in 1970 to fully commercialization by Chevron in 2004. The main targets are Q2 to Q6 sand sequences. Q2 and Q3 sand sequences are main targets of A12A CPP-A1 well, which have 99.95% of methane gas. The well is currently producing. Drilling operation summary. The Q2 sand sequence was drilled deviated while Q3 sand sequence was drilled in lateral part of 8.5 hole section. The TVD at total depth is 572 meters. The stabilized LWD Ecoscope tool was run in 8.5 hole section to acquire measurements. The bottom quadrant density data was used for evaluation purposes. Literature review. Literature review involves major LWD tool physics, their working principles, application, and their limitations. The second part of literature review involves effect of presence of clay on effective porosity, saturation of water, and finally, original gas in place. Software methodology. LogIC software is used for the processing of raw log data. The standard workflow involves selection of appropriate analysis methods to calculate volume of clay, effective porosity, and saturation of water, and apply their cutoffs to finally get the pay zone thickness. Q2 and Q3 sand sequences are zoned based on different physical and lithological properties. Analysis methods. To apply suitable analysis methods, Q2 and Q3 sands are classified into two different sets based on similar physical and lithological properties. Porosity is calculated using neutron density equation. Volume of clay is calculated using gamma ray. Hydrocarbon correction is not applicable in case of LWD. Total porosity and effective porosity is calculated using the equation given in this slide. Attenuation 40 inches, 2 megahertz is used as a true resistivity formation. Saturation of water is calculated using Indonesia equation to compensate for the conductivity of shale and silt present in the lithology. Resistivity and saturation of flush zone is not applicable in the LWD case. Bottom hole temperature is calculated using temperature gradient of offset well. Hole was gauged, so bad hole criteria was ignored. All the parameters for the second set are same as the first set of zone, except volume of clay is processed using either density neutron or average of gamma ray and density neutron to compensate for the high radioactive mineral effects. Attenuation 22 inches, 2 megahertz is selected as a true resistivity formation for Q31 base sand and for Q32 reservoir. Assignment of petrophysical parameters for true response. The average matrix grain density response is 2.67 gram per cc, whereas the density and its corresponding neutron porosity response is selected from this shale point indicated on a density neutron cross plot. The neutron porosities are displayed on limestone compatible scale. Because of the mixed lithology, the bottom quadrant photoelectric vector response is 2.5 for sandstone. From gamma ray histogram, the sand line is selected as 65 API, while the shale line as 135 API. The bad hole criteria is given in at the bottom. The resistivity of formation is extracted as 0.192 ohm meter from 18 meter thick, clean, water-bearing sand zone using Pickett plot. Using these cross plots, 20% cutoff is defined for effective porosity, whereas 70% cutoffs are defined for volume of clay and saturation of water. Manual methodology. To cross-check the software computed results, following manual methodology is used. Outputs from offset well. LWD attenuation 40 inches, 2 megahertz. Resistivity is comparable with offset wells wireline data from Q21 to Q31 lower sand sequence, whereas the 22 inches, 2 megahertz resistivity is comparable with wireline data of offset well from Q31 base sand and Q32 reservoir, as we could see in the figure. The bottom hole temperature is calculated as 20.8 degrees centigrade from offset wells temperature gradient of 2.76 degrees centigrade per 100 meter. The average grain density of matrix is 2.67 gram per cc, is determined by averaging grain density data of offset well. Results. Following are the average evaluation outputs of net to gross ratio, volume of clay, effective porosity, and saturation of water per each zone as given in the figure below. Then the average original gas in place per unit area in metric and field unit system per each zone are then determined from the average evaluation outputs that were generated from software. The total original gas in place of entire well at reservoir condition in field unit is 643,996 cubic feet per acre. The average volume of clay, porosity, saturation of gas, and original gas in place per unit area in field units using manual methodologies are given in the table below. The manually calculated total original gas in place per unit area for entire well has offset of plus 0.12 cubic meter per meter square. This difference could be because of rounding off the digits, averaging the values, and difference in software applied algorithms. Discussion and interpretation of results. The top part of Q21 reservoir is a very good candidate for perforation because it is separated by shale break and there is no danger of water encroachment, whereas the basal part has close gas-water contact, so it may be considered for perforation at later stage of production. The top four packages of Q22 reservoir are pay zones, whereas the package 5 is non-pay zone. The top three packages can be considered for immediate perforation. However, the relatively thin, the fourth package has gas directly on the top of high saturation of water. So this should not be considered for immediate production. This is a good sand unit for perforation, and the high gamma ray reading could be because of presence of radioactive minerals such as mica. These both sand units of Q31 zone are good candidates for perforation. However, the upper Q31 sand unit can be questionable because of its close gas-water contact. Because of good saturation and porosities, the top three layers may be considered for immediate perforation, whereas the relatively thin package 4 should be considered for perforation at a later stage of production, and package 5 should not be perforated because of the close gas water of high contact of high saturation of water. Similarly, the basal part can be considered for immediate perforation, whereas the thinly laminated 2 layers above this basal part should not be considered for immediate perforation because of the high saturation of water. Without any question, this is a good candidate for perforation. Q32 reservoir zone is the main reservoir zone of this well and is placed in lateral section of well. Because of the loose silty sand, the open hole production should not be taken to avoid sanding issues. Conclusion. After applying the appropriate cutoffs, the cumulative actual vertical pay zone thickness is 24.22 meters. The variation in physical and lithological properties provided basis to evaluate zones separately. The average effective porosities ranges from 30 to 35%, whereas the average gas saturation ranges from 47 to 74%. The net to gross ratio ranges from 53 to 88%. The cumulative original gas in place at reservoir condition in field units is 643,996 cubic feet per acre, whereas manually calculated original gas in place per unit area has offset of plus 17,290 cubic feet per acre. This offset may be because of the rounding of the digits, averaging the value of difference in software calculation algorithms and formulas applied in the software. Based on evaluation outputs of effective porosity, saturation of gas, net to gross ratio, and original gas in place, the well has fair section of producible sands, so therefore it can be considered as a good producer. Recommendation. The following are recommendations for the case of thin reservoir and horizontal well. The pilot hole wireline resistivity may be reliable to select true formation resistivities. In case of absence of pilot hole, offset wells wireline data can be compared for the selection of true resistivity of formation. LWD propagation resistivity processing, such as Merlin processing, can be used to remove the discrepancies in the data. The blended resistivity may also be used can be used in such a cases. Top and bottom of reservoir zone can be determined by knowing the coarsening and fining upward stratigraphic succession. In case of water-based mud, lateral log tools can provide more reliable true resistivity formation comparing to propagation resistivity. The forward modeling based on offset well data can be used to ensure reliable well placement. References. Following are the references that are used in the preparation of this presentation. Thank you for your time. If you have any question, you're welcome to ask.